Oh, so the Laplace transform, what about that? Okay, so the Laplace transform gives rise to a whole new world in mathematics. Gives rise to what we call operational calculus. You guys know about differential calculus and integral calculus. This new world of mathematics is called operational calculus. What do we do? Well, so there's a bunch of transforms out there, not just the Laplace transform. But what is it? So a transform a function from one domain to another domain. All right. Well, there are actually differential transforms, that are integral transforms, and many other transforms. But these transforms we are interested in. It's an integral transform, okay, which is given in terms of the integral from 0 to infinity of e to the negative sc f of t dt, where the function f of t, it's the function we're going to transform. Now, guys, in general, transforms, or more specifically, transforms have the following look here. So it's a new function in a new domain, some function f of u, which is some integral from 0 to infinity or whatever that is of some k of x u f of x dx. All right. So again, the function f of x is the function to be transformed to another domain. But what is this k of xu? Notice this is a function of two variables here. Okay, let me actually highlight it and relate. So this k of xu, it's what we call the kernel of the transformation. So in linear algebra, the kernel, it's actually the set of all vectors that map to the zero vector in the codomain of a transformation. Well, if you're taking linear algebra, right now you will eventually get there. All right. So the kernel for the Laplace transform, it's this exponential function e to the negative st, which happens to have two variables, right? Instead of x u, it's a function of s and t. All right. So what are we going to do? We're going to transform a function from the world of t to the world of s. In applications, specifically in electronics and electricity and magnetism, this actually works to transform a problem from the analog world to the digital world. That's one of the applications. All right. Okay, notation for the Laplace transform. So we use this curly L, this fancy L, which looks like the Lagrange function from calculus 3. It's the same L. And what does it do? So the Laplace transform of some function with lowercase becomes a function of uppercase of the same letter. Laplace of f of little f is equal to big S. Laplace of little g equal to big G, etc. All right. So let's evaluate some Laplace transforms here. The Laplace transform of a number. Okay. So in this case, f of t, right? F of t equals to 4. So this will be the integral from 0 to infinity of e to the negative st times 4 dt. All right, which is the same as saying, check this out. Let me take out the 4 outside of the integral and then write the integral from 0 to infinity of e to the negative st dt. And guys, the purpose of evaluate or the objective of the Laplace transform initially is to compute this improper integral. However, I'm going to take a different approach, and rather than evaluating, than setting up a limit problem, upper limit, minus lower limit, and all that, how about we just use the gamma function to make this way quicker? But wait, this doesn't look like an integral that can be evaluated using the gamma function. Well, check this out. Do you guys agree that this is the same as saying 4 times the integral of 0 from 0 to infinity of t to the 0 power? e to the negative st dt. All right. Do you guys agree with that? I mean, t to the 0 equals an invisible 1 in the integrand. Okay. So using the gamma function, uh, this would be 4 times the factorial of the power of t, which is 0 factorial, over, well, actually, n equals to 0 and a equals to s. All right, so what do we do? Uh, a, which is s to the n plus 1, 0 plus 1, which is for 0 factorial, that equals to 1 over s to the first power, which is 4 over s. All right? So what did we have? A function of t. And we created a new function, a function of s. All right. In general, okay, let me show you the table of the brief table of Laplace transforms. Okay. On the third page, we have the formulas for the Laplace transform. So every time we want to find the Laplace transform, oh, I don't think I write it. I wrote it here. The Laplace transform of a constant a. All right. This is equal to simply the constant divided by s. So that means the Laplace transform of 5 is 5 over s. The Laplace transform of 6 is 6 over s. The Laplace transform of 10 is 10 over s. I'm going to show you the derivation of this one in a way. All right? Okay. Let's find the Laplace transform of t. That is f of t equals to t, which is the integral from 0 to infinity of, what is that? T e to the negative st dt. All right? So what do we get from here? This is, how about again using the gamma function? The reason why I wanted to use the gamma function, because remember how it was a quick way to evaluate these integrals? Because otherwise, that would require us to use integration by parts, all right? And that could be somewhat tedious. So a equals to s and n equals to invisible 1 right here, all right? So what is this? 1 factorial divided by s to the n, which is 1 plus 1. That is 1 factorial. What is 1 factorial? That's also 1 divided by s squared. All right. Let me show you another example. F of t equals to t cubed. All right. That equals the integral from 0 to infinity of t cubed e to the negative st dt. Okay. All right, guys. So again, think about evaluating that integral. Do you guys agree we would need to use integration by parts 3 times, and then on top of that, setting up an improper integral for every iteration? Can you guys envision the amount of work for that? But we have gamma function here that is n equals to 3, that is the power of t, and again a equals to s. All right. So this will be equal to the factorial of the power, that is 3 factorial divided by a, which is s, raised to the n, which is 3 plus 1, which is 6 over s to the fourth power. All right. Well, of course, we don't have to do all of this using the integral. Again, there are formulas, okay? So let me show you the formula here. So the Laplace transform of some power function t to the n, so n factorial over s to the n plus 1, that's all we need, all right? That's actually, it's the result of using the gamma function that I showed you in the previous funky section, right? Okay, so now, what is the exponential one? For this one, I'll have to do the improper integral. So in this case, f of t equals to e to the 3t. That's the integral from 0 to infinity of e to the t, e to the 3t, e to the negative s t dt. Well, in this case, we have a product of exponentials. I'm going to combine them into one single. That equals the integral from 0 to infinity of e to the I'm going to write 3t minus st dt. And I'm going to factor out the t because that's actually the variable with respect we're integrating, right? So that's the integral from 0 to infinity of e to the, let me do 3 minus s t dt. But actually, I'm going to go and rewrite this in terms of, I'm going to reverse the order of the terms here. That is the integral from 0 to infinity of e to the negative s minus 3 t dt. Well, we're just integrating an exponential of the form integral v to the at dt equals 1 over a e to the at plus c. Well, in this case, this is a definite integral. So we don't need to show the u substitution for this one. So that'll be uh, negative 1 over s minus 3 e to the negative s minus 3 times t from 0 to infinity. All right. Okay. So what's this? Okay, upper limit minus lower limit. And again, I'm just going to use upper limit minus lower limit without setting the limit notation here. So 1 over s minus 3. This is e to the negative s minus 3 times infinity minus e to the negative s minus 3 times 0. Well, where does that term go to? Where does that go to? 0. Where does that go to? 1. E to the 0 equals to 1. All right, so we're going to be left with negative 1 over s minus 3 times 0 minus 1. Multiplying the signs, we get 1 over s minus 3. All right? That means the Laplace transform of e to the at equals simply 1 over s minus a. All right? So rather than going through the integral, we're just going to use the formula. Well, that formula is, where's that formula? The formula is right here. That's letter B. That's the second formula. All right? Okay. Oh my God, the next one, the Laplace transform of sine and cosine. Okay, check this out. Okay, guys, check. What if, well, let me actually do it up here. So that'll be the integral from 0 to infinity of sine kt, okay, e to the negative st dt. Guys, this integral is a nightmare to evaluate. So if you remember this integral from calculus 2, it's one of those integrals that actually took a page or a page and a half to evaluate, and it goes like in a loop. Eventually, you get back to the original integral. You have to treat the problem like an equation. And to be honest, guys, I don't have time to. Well, I have time, but I don't want to do it like this, right? I'm gonna use complex analysis to get these transforms very quickly, and not only that, I'm going to get the Laplace transforms for both functions in one shot. All right? Check this out. So, did you guys agree that, oh, you guys remember this identity here, right? Cosine kt plus, no. Cosine t plus I sine t. Isn't that equal to e to the it? Is that Euler's identity? And you can always change the angle if you want, all right, to cosine kt plus I sine kt, which is e to the I kt. All right? I mean, 2t, 5t, whatever. But in this case, we want kt. All right? So, one thing to keep in mind, check this out. Do you guys agree this is the real part? This is the imaginary part? Okay? How about we take the Laplace transform of this equation here on both sides of this identity? Take the Laplace of this guy. Yes, I would be taking the Laplace of cosine kt plus the Laplace of I sine kt. But instead, check this out. I'm going to take the Laplace transform of e to the I kt, which is the integral of, well, actually, how about we just use, I'm not even going to set the integral. I'm going to use the formula from before, the Laplace transform of e to the at equals 1 over s minus a, which is 1 over s minus ik. How about that? And that's the Laplace transform of sine and cosine combined. But check how we're gonna get this. So remember when we were working with complex numbers, we didn't want these i's in the denominator. So I'm gonna multiply numerator and denominator by by the conjugate, s plus ik, s plus ik. All right. In the numerator, we end up with, what is that? S plus ik divided by, do you guys agree that this is a difference of squares in factor form? Okay, this is s squared minus ik squared. Okay, guys, what is I squared? Does anyone remember what's I squared? 1? Negative 1 times this negative, what is that equal to? Positive, is that s plus ik, s squared plus k squared. And I'm going to split these two into real plus I imaginary parts, all right? So this is s over s squared plus k squared plus I times k over s squared plus k squared. This is the real part. This is the transform of cosine. And the imaginary part is going to be our Laplace transform of sine kt. Like a box, right? The two transform in one shot, right? In one, rather than evaluating that hell looking integral. I mean, you want to do the integral, but that's fine. You should get the same result, that's fine. But sometimes using uh, these tools help us actually solve some problems in a way quicker way, right? There's another way to get this. Well, I'm going to do this maybe after the examples. All right, so let's have a look at the example. So forget about the integral, the improper. Let's just use the formulas. So these are formulas that we're going to use to get these transforms, okay? So find the Laplace transforms of the given functions. Okay, so the Laplace transform of 4e to the 2t plus 3t to the fourth minus a. So this time we're going to use the Laplace transform of an exponential function, which is this formula here, the Laplace transform of a power function, which is this first formula there, and the Laplace transform of a constant, which is the constant over the variable x. All right. Now the Laplace transform, before getting to the Laplace transform, the transform is linear because if you have the Laplace transform of the sum of two functions or the difference between two functions, you can take the Laplace transform individually, which is what we're going to do. All right. So what does that mean? So this is 4 times the Laplace transform of e to the 2t plus 3 times the Laplace transform of t to the fourth power plus minus 8, or rather minus the Laplace transform of 8. And just using the formulas, okay, all we do, this is 4 times 1 over s minus a. But what's a in this case? The quantity that multiplies the t in the exponential, s minus 2, plus 3 times the transform of t to the fourth. Okay, so for the power function, that is n factorial, which is 4 factorial divided by s to the same power plus 1 minus the Laplace transform of a number. What's the Laplace transform of a number? It's just the number over s. 8 over s. And that's the transform. No more integrals, no more gamma function, just formulas, right? So Well, at least let's simplify this a little bit. So this will be 4 over s minus 2 plus, okay, 4 factorial. What is that equal to? 4 times 12 times 2, 24. 24 then times 3, is that 72? 72 s to the fifth power. My s's sometimes look like 5s, all right? This is s and this is 5. And then minus 8 over s, all right? Now let's find the Laplace transform of 2 cosine, okay? 2 cosine 5t, 7 sinh 3t. So for hyperbolic functions, well, actually, I didn't do the derivation for the hyperbolic one. But actually, the sinh and the sine, they look very similar except for the sign in the denominator. Same for the cosh. Cosh has a negative in the denominator, unlike cosine, its trigonometric analog, which has a plus in between the terms. Okay, so okay, so let's find the Laplace transform of cosine. Okay, the cosine has an s in the numerator, unlike the sine function has a k in the numerator. That's how you can distinguish between the two. And that's the same for the hyperbolic versions of them. So this means 2 times the Laplace transform of cosine 5t plus 7 times the Laplace transform of sinh 3t. Okay? So the cosine is the one that has the s in the numerator. So this will be 2 times s divided by s squared. And what do we do? Here, k equals to 5. We need k squared, which is 5 squared. But what's 5 squared? Well, we can compute it later. Plus 7 times the transform of sinh, which is k over s squared minus k squared. So in this case, that's k, which in this case is 3, over s squared minus 3 squared. Simplifying all this should give us 2s divided by s squared plus 25 plus 7 times 3, which is 21, over s squared minus 9. All right. So what's next? One more. How about the transform of square root of t? So, number one, this is the same as saying the Laplace transform of t to the 1/2. Okay? But guys, in this case, we would need to use the factorial of a half, right? We can evaluate just the factorial of 1/2. How do we do? Well, 1/2 times negative 1/2 times negative 3. No, that's not how we're going to evaluate. That's where we're going to use the gamma function. All right. So this would be essentially, check this out, 1/2 factorial divided by s to the n, which is 1/2 plus 1. For the denominator, we're fine. S to the 3/2, that's fine. But what about the numerator? We need to spawn the gamma function here. Okay, let me write it down again. So gamma, keep in mind that gamma of n plus 1 equals to n gamma of n. All right. So um, this is okay. This would be the same as saying gamma of 1/2 plus 1. All right. That's for by definition of the factorials. And then using the gamma function, this is 1/2 gamma of 1/2 over s to the 3/2. But again, what's gamma of 1/2? Square root of pi, right? So this will be equal to 1/2 square root of pi, right? 1/2 square root of pi divided by s to the 3/2. All right. So there's a couple of ways to keep rewriting this one. So I'm gonna rewrite this as a square root of pi divided by 2s times s to the 1 half. All right. Do you guys agree? 3 halves is s to the 3 halves is the same as s times s to the 1 half. Add the exponents together, invisible one. Okay. So, and also this is the square root of pi over 2s square root of s, which is 1 over 2s times the square root of pi over s in one single radical. However, this is good enough anyway. But if you want to go a bit further, that's fine. All right. Maybe actually let me bring down this 2 in the denominator here to make it look nicer, much better. All right. Okay, guys. So, I mean, for the take-home quiz, I'm gonna give you today. You're not gonna do anything using the integral, the long method. No, you're just gonna use some. I mean the definitions, the formulas here. I'm gonna give you some kind of funky functions, but I'm gonna give you hints on what to do first because the way the functions I'm gonna give the way the functions are gonna be given are not to directly find the transforms. All right. Okay. So actually. Before we go, okay, the next topic would be about existence of the conditions for the existence of the Laplace transform. However, I don't think I'm going to have enough time to cover this right now. Instead, I'm going to show you a different way. Yeah, let me go back to the Laplace transform of sine, okay? So because I feel like I will have time for the Laplace transform of sine in a different way rather than the existence of the Laplace transform. Okay, so let's say, okay, another way. Go back to page 2 at the end of the derivation. Okay, so another way, let's say we want the Laplace transform of sine kt, all right? Okay, so let me actually highlight the argument for a big reason, okay? The angle, if you will. This is the same as finding the Laplace transform of sigma n equals 0 to infinity of -1 to the argument to the n to the 2n plus 1 divided by 2n plus 1. So what we're going to do is we're going to use power series representations of function to take the Laplace transform of this, right? So this is the same as saying kt here. All right. The -1 to the n. Yes, thank you. So let me distribute the power, so to speak. Okay, so what do we have? Okay, so we have the Laplace. Okay, instead, I'm gonna do sigma n equals 0 to infinity of -1 to the n power. I'm gonna take the Laplace transform of at to the 2n plus 1. All right, over 2n plus 1 factorial. Okay, let me actually, okay, because this is constant here. Well, we're taking the Laplace transform of the variable t. Right now, k and n are constants at this point. All right, so this will be sigma n equals 0 to infinity of -1 to the n. Laplace, okay, I'm going to take, okay, the Laplace transform of k to the 2n plus 1 and times t to the 2n plus 1. All right. This is constant. I'm going to take it outside of the Laplace transform over 2n plus 1 factorial. Okay, so essentially all I'm going to do here, I'm going to take the Laplace transform of the function of t. That's a power function, right? Again, let's recall that the Laplace transform of t to the n equals n factorial over s to the n plus 1 power, right? So that means, check this out. That means sigma n equals 0 to infinity of -1 to the n, k to the 2n plus 1. So this power factorial 2n plus 1 factorial divided by s to the 2n plus 1 plus another one integer for the plus 1 factorial here. That is 2n plus 2. You guys agree with this so far? Okay, everything divided by 2n plus 1 factorial. All right. With what is good here, though, is the following. 2n plus 1 factorial goes away with 2n plus 1 factorial. All right. And I'm going to break down this k to the 2n plus 1 like this. This will be sigma n equals 0 to infinity, negative 1 to the n, k to the 2n. I'm going to write this, okay, I'm going to write this as a k times k to the 2n divided by s to the 2n times s squared. This s to the 2n plus 2 goes to the denominator, and at the same time, I'm writing this as s to the 2n times s squared, all right? Now, I'm going to work with the series only. In this case, the variable for the series is the variable n. So I'm going to take everything else outside. So k over s squared goes outside, and that is check this out. This will be negative 1 to the n, k to the 2n over s to the 2n, which is k over s squared sigma n equals 0 to infinity of negative 1 to the n. Okay, do you guys agree with the following? This is the same as saying k over s squared to the n power. All right. So I'm keeping the second power for the s. I'm just taking the n power. And now check this out. Do you see this common power here? The power of n? I'm going to group everything into one single parenthesis. All right. So this will be k over s squared sigma n equals 0 to infinity of negative k over s squared to the n power. Guys, does that series look familiar for you? Something raised to the n? Geometric series, right? Geometric series. Okay, what about geometric series? Whenever you have sigma n equals 0 to infinity of u to the n, this is 1 over 1 minus u. Remember the formula to find the sum the all the infinite terms of a geometric series, provided of course u is between it's a number less between 0 and 1, right? Excluding the of course, right? Okay, so I'm going to rewrite this instead. K over s squared 1 over 1 minus u. But what's u? Isn't that u? Negative 1 over s squared. Okay, and then by the smile rule, right? Smile, be positive. All right, k over s squared 1 over s, oh wait, 1 over 1 plus 1 over s squared. Okay, and I'm just going to multiply this across. This is 1 times k, which is k, divided by s squared times 1 plus 1 over s squared. Wait. This one's supposed to be a k here, right? K, forgot the k. K. And well, s squared times 1, isn't that s squared? Plus s squared divides out here, and that was supposed to be a squared here. Shoot. Okay, but you got this, right? Squared, 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 plus k squared, and that's another way to get the Laplace transform sine. And you can do the same one for cosine. You can do the same thing for the exponential. For the arctangent, just wait for that one. All right.